All right. Hi, everyone. Welcome to the live coding session for HDSC Data Science. Okay. Yeah, I can see you guys. Can see Bruno, Samuel. Welcome, guys. Duncan. Wow. Interesting. Someone's name is iPhone. Someone's name is iPhone. Okay, I can see Gael. I can see Praise. I can see Toluwani. I can see Wellspring. Wow, that's so English. I can see Adeleke, David, Alamu. You guys are all welcome. Welcome to PhD, the live coding session. My name is Goodrich Okoro, and I'll be your instructor, basically taking you through some practical sessions, right, for the stage C. So you feel free to ask questions wherever you don't understand. And yeah, we can just deliberate on that and share more ideas. Okay, I'm going to present my slide. We'll just go through some few slides, then we jump into the notebook. I've not heard anyone say anything. Can you guys hear me?
Yes, we can.
Yeah, we can hear you.
Can hear you.
Okay.
We can hear you. We can hear you.
All right, cool. Let me just share my screen. Give me a sec. Okay. And you see this introduction to linear classification. Can you guys see the introduction to linear? Can you see my screen?
Yes, we
Yes.
can.
Yes, we can see your screen.
All right. So we are going to be having four classes. Today is the first one. So it's just going to be the breakdown of what you have in the course content on the Harmony space. So today we'll just look at introduction to classification, get to know some terminology and yeah, what it's all about. I believe your previous stage was where you did regression, right? And regression is just about not about numbers and how linear they relate to each other, the predictor and the target. So it's like you're predicting numbers or some sets of figures. But here is classification where you're looking at categories. Is it red or blue? Is it black or green? Is it one or zero? Right. So I'm going to move on to the next slide. So yeah, we want to navigate through the topic and yeah, understand the theoretical aspect of it. Then in the next few minutes we jump into the notebook and just do a little practical, right? So at its core, linear classification is about drawing boundaries, right? So imagine a set of data points. You can see the image to the left belonging to two different categories. Our goal is to find a line or a plane that separates the categories as clearly as possible. Right? We are more after that line that can separate them as much as possible. So that line is actually called the decision boundary, and it's the heart of linear classification. Okay. So we have different classification techniques. I think we'll see those ones in the consecutive classical support vectors, electric regression, which we are going to see some of them today. Right. Yeah. So why does this concept matter? So understanding linear classification and predictive regression is actually crucial in any machine learning field, and it's actually the building block for more complex algorithms and are widely used in applications, right, ranging from farm detection to medical diagnosis. So our focus today, we are just going to dive deep into some principles and we'll explore how to use some data and do some classification. Okay, so the real world implication of techniques are very, very wide. And whether we are analyzing customer behavior, credit scoring, sentimental analysis, the insights we can get from this kind of classification can help us make some data-driven decisions that can help businesses and also improve life. Okay, so what are the core concepts of this linear classification? I talked about some of this stuff, the support vectors. Well, we're going to be using the cited library to do the practical aspect of it. And we'll see how it works. I talked about the decision boundary. So it's just the line that separates the two points we are trying to work with. And we have some examples of linear classification. I already mentioned that some few seconds ago, the support vectors. They are very powerful linear classifiers that they don't only seek to separate the clashes with a line, but they also aim to do that with the maximum accuracy as much as possible within the boundaries. We also have logistic regression, and it gives extensively for classification tasks. It predicts the probability that the given data belongs to a particular class. That's what logistic regression does. It helps predict the probability that, oh, this one belongs to this one by, let's say, 90%, or this one belongs to this one by 30%. So it just predicts probability that the given data point belongs to a particular class. We have the perceptron, simple yet effective classifier that updates the system boundary repeatedly, adjusting it based on the data points it misclassified during training. Yeah, I think we are going to be using some scikit libraries to work on the practical aspect of it. We'll bring in the whole model and yeah, we'll train some data set and see how it works. Time is running. Let's expand more on the logistic regression. Pardon me, it's more like we all know how it goes, so we just go to some theories. If you have any questions, you can just ping me or you just alert me. And after the theories, we'll jump into the data book and just do some practical. Okay, so yeah, logistic regression. It's designed to predict the probability of a particular outcome, like I said. So, for instance, in a medical diagnostic scenario, logistic regression can predict the probability of a patient having a certain disease based on some various predictors like age, blood pressure, and cholesterol levels. Right? If you go to a hospital, maybe you've trained your model using several data that has all these parameters, age, I don't know, maybe your blood level and the rest of them. If they find out that you fall within maybe the class of people that usually that with a combination of some factors, they have such disease, and then they just put your own details into the system. It's just, oh, this person is likely having this kind of disease. So that's what predictive probability means. Binary classification. Yeah, we also have the sigma function mapping the probabilities. That's the S shape you're seeing to the left hand side. It takes any real value numbers and map it onto the value between 0 and 1, effectively translating the linear output of the model into probabilities. So it's either on the side or it's on the side and how close it is. Now, how do you understand the output? The output of logistic regression offers a probabilistic interpretation. The prediction of zero point 0.8 from our model, for instance, suggests an 80% probability that the data point belongs to the positive class, right? Just like I said. We also have hold on. Okay, I've talked about the output. So you have it in decimal numbers, which is like percentage. You also use threshold. Maybe setting it to 0.5. If you can have a threshold. If the predicted probability is greater than 0.5, then the data point is classified into the positive class. Otherwise, it's classified into the negative class. So this threshold, I think they usually use this mostly in the lending industry, where maybe before they give out loans to customers, they obviously your details will go through some lending models, right? with your information, your lending history, credit history. If you fall into a particular category and your maybe the output of your score is within a particular threshold, they can classify you as someone that is likely going to take a loan and not return it. So yeah, they also make use of this stuff. I'm going to go on to the next slide. Hope you guys can still hear me. Can you guys still hear me?
Yeah, we can. We
Okay,
can
cool.
hear you.
So we talk about the data preparation for logistic regression. We're going to focus on just three essential methods. More like the things you need to watch out for, most importantly, handling missing values. We're all data science students, so we know what it means by handling missing values. We know that if you have take for instance, if you have, let me just do some practical, yeah. I'm not going to do a simple scenario with an average. Say you have oh hold on, what's it, zero? Let me just say one, two, three, four. Oh, I don't think that's what I wanted to do. Come on, let me just give a practical example. Because it shows what the missing value can cost if you don't handle them properly. You're not going to give us some wrong results if you don't handle them properly. Okay? Not difficult network. Okay. Bringing out zero as the mean of that value, which doesn't really make any sense. Let me use it for 1, 2, 3, 4, 5, 6, 7, 8. Still giving us a zero. So yeah, this is what you're likely going to maybe encounter if you don't take care of missing values, because as it stands now, the list has some missing values. It has some missing values here. And if maybe you are not aware, and you're trying to maybe look for the average of this column, which was what I was trying to do. You see the result, it's giving back. It doesn't really make any sense. But once you handle the missing value and maybe you have the same output, and who knows what you're doing, maybe you replace it with the average or the mode, whichever one is your implication. But let's say I replace all of them with zero, since it's a numerical field, the results you're going to have is going to be different. Sorry. Uh, but you see, the result is actually different. So handling your missing value is actually very important. Once you have it, it's likely going to cause an issue for you. And yeah, once you take care of it, you're likely going to be having good results. Then we have, hold on, I'm not done with this. We have the encoding categorical variables. We all know that there are some models that doesn't accept values. Sorry, I mean text. They don't accept text, right? So you just need to encode them. So it's like converting categories to numbers. So like this logistic regression, for instance, it doesn't accept categorical variables in the form of male and female or yes and no. It must be converted into numerical values for the model to process them. So we have the one hot encoding that we can use to do that. So that's one of the one common technique. So it creates a new binary columns for each category. So if you have male and female, it's probably going to turn it to one and two. But if you have up to three categories, it's probably assign one to three to each of them respectively. So this approach ensures that the categorical data is suitable for the model, formatted for the model to work with. We have the spelling features. Sometimes you could have values that are large, especially in the finance industry. That's why most times we usually normalize the data. You could have one, all of a sudden you're seeing 2,000, all of a sudden you're seeing 30, all of a sudden you're seeing 1 million, all of a sudden you're seeing 400. So these the ranges are just wide and broad, and maybe you have another column with far greater number. So what we do is to normalize it, let them all have a common base, probably within 0 to 1, depending on the weight they all carry. So we normalize that for the model to train better. So uniformity in data is about bringing all variables onto a similar scale. So this uniformity is actually important for linear regression to convert more smoothly and for the model to treat all features equally, especially when they vary in units or magnitude. We have the mean max scalar, we have the standard scalar. So the mean max scales the data within a specified range, often 0 and 1, once you apply that mean max scalar. While the standard puts it into standard features by removing the mean and scaling the unit variance. All right, so why does this whole data preparation matters? We're 15 minutes in already. Okay, I'm just going to be quick. I don't want to spend too much time here. So it's actually very important to handle all the stuff so that the model would work properly. We have the model evaluation. This is how you know if your model is performing well. We have the accuracy, represents the overall correctness of the model. I have to define because of time. You have the precision. It measures the accuracy of the positive predictions, right? So it's actually the ratio of the ones that was predicted correctly to
Hi,
the
sir.
total. Yeah, I can hear you. Any question?
The sound is not really very clear. I think others are also complaining in the chat, so I don't know if you can
Oh,
adjust that.
okay. Sorry about that. Sorry, sorry. Can you hear me clearly now? Just hope it's better now. Okay. Sorry about that. We
Yeah,
have the
better.
yeah, recall also known as sensitivity. It measures the model's ability to identify all the top positives. And we have the other ones, precisions and recall. And evaluation is actually very important. It's how one would know if your model is doing well or not. Then we have multi-class. This is where we are trying to classify just beyond two categories. We have the multi-class classification. So it's just beyond two class problem. Then we have different classification method. We have the one versus direct, also known as one versus all. It involves decomposing the multi-class classification problem into multiple binary classification problems. Then we have the one versus one. Most of this stuff it's broad. Probably need to go and expand our knowledge on them, but yeah, these are like the different multi-class techniques you can apply. We have the one versus one strategy. So it takes the approach by training a binary classifier for every two
Hello,
edge
sir.
cases.
Can't hear
Hello,
you. The
sir.
volume is very low.
We can't even hear you again. No.
Oh,
Yes, we can't hear you again.
I don't know. This is my network. Can you hear me now? Is it better now? Is it
Yes,
better
it's
now?
better now. Yes,
Yes,
it's now
it's a bit
better.
better. It's a bit better.
Sorry about that. All right, so you just need to expand your knowledge on this and watching time. We have the techniques. These are regularization techniques, and it's used for enhancing our model performance. We have the lasso and the reach. I think Someone start the recording. Okay. Hold on. Let's check something. Yes. Okay. All right. We have the reach and the lasso method. So what the lasso does is add penalty equal to the absolute value. And we have the shrinking coefficient. That is the reach. This is when we want to retain all the features but reduce their influence on the outcome. We use the reach method. While the lasso can also perform feature selection by eliminating features that are not um probably helping in predicting the target. I think we have a class where we will focus more on this session, then we'll deliberate more on it. So today is more like an introduction to everything. Then we have the comparing of linear classification method. Sorry, I'm trying to rush because it's already past 20 minutes. And yeah, the conclusion. So it's basically what we've walked through the different types of classification, the multi-class, the technique, right? The evaluation of our models, the prediction, guys, the recall, accuracy, and the rest. Okay. I don't know if anyone has any question on the slide, but I would love to jump into the practical parts now. Does anyone have any question for me? Okay. All right. So I'm just going to quickly bring in the models.
Hello?
Hello, can you hear me? Can you guys hear me?
Please, the your Google Colab is in dark mode, so we cannot see.
Goodrich, your voice is
All right.
breaking.
So I'm just going to quickly bring.
And you can please increase the fonts of the Google Colab, please. It's a bit tiny. Thank you.
Hello, please.
Can you guys see it now? Is it clear?
Cannot see. Goodrich, your voice.
I've actually zoomed in. It's still not clear.
Yes, please, it's better. Thanks.
Um, is it better now?
Yes, it's better.
So I'm going to quickly bring in what we want. Just give me a second. Sorry. Oh my god. But I'm probably just going to bring in everything at once. We are going to be using an inbuilt data set, but I wouldn't have time to start looking for one now. Yeah, we're going to work with an inbuilt data set. Mhm. Mhm. We'll bring in our participant. Okay. Sorry, I'm in a hurry, guys. Not a mistake. Okay, let's quickly load our data set. Cut off time. Okay. All right, so these are the models we need, the libraries we need, and this is me actually I want to make use of the iris data for this class. I want to make use of the iris data for classification. So this is just me using an embedded data set. So I've loaded it in. It contains the data itself and the target we want to predict. I don't know if we are all familiar with the iris data set, but it's about flowers. We have three different flowers for the iris data set. We want to see how we can classify the three of them. Okay, so I'm just going to do this. That's for our data. Then our test data. So X is holding our normal data while Y is holding our target of data. And we know that in machine learning, we have what we always want to predict. So Y is holding that, Y X is holding our normal data. So we are going to load in our model now. And then we split our data set into training and testing. Split it. Let's split the test. Okay. So what I'm doing now, I'm just splitting the data set into training and testing data using the library we brought in. Okay. Um, we can do it. Let's split it 70-30, or we can do 80-20. So we're going to set the test size to 0.2. So this means that the testing data would be 20% of the entire data, while the remaining 80% will be used for training. Then we need to set the random state so that in case we run it, we always have the same output. So we are going to train the model. I've loaded in the model the logistical regression. Now I want to use the training data set to train it. Okay. Okay. So we need to set the maximum iteration. I think it has a limit at which it converges. So you need to set how many times at what iteration it's going to converge. Uh, let's set it to 200 and okay, that works. So what we've done, we've used the training data set to train the model. So the aim here is to be able to classify these flowers from the iris dataset correctly. Okay, so if after training this, let's just see what it will look like when we use it to make prediction. So we've trained the model. We are now trying to use this model to see if it will be able to predict the test data we had. So I'm going to just pass it in. Okay. So why trade now is holding the prediction, and these are all numbers. These are all numbers. So let's say each of these represents each flowers. I think I read some of them somewhere. Let me check my book. I wrote that somewhere. We have the we have red color, and we have the writing the benefit. These are the three flowers we are trying to predict, and I think I'll explain more when we look at the transition metric. Okay, so let's see how accurate these results are. Actually, we're breaking the accuracy score, but then that's so let's check the accuracy now. We'll compare what it has predicted to the original data set. This score is very high, and it looks like the model is overfitting. The accuracy is 1, and that's so accurate. Like, it means the model is obviously overfitting, and I don't think our data set has much context. So it's not much. Okay, let's just see what the question report to say. Wow. Okay, everything here look very accurate, and I would say this is as a result of our data set being very small, but the accuracy here and everything is so accurate. And I'm not saying this is how probably your own result is going to look if you're working with a different data set. But as it stands now, checking the length of data set I'm currently using, it's just 115 length. So there's every tendency that it's overfitting. When I mean it's overfitting, it doesn't have enough data to work with. So it's very small, and it's like passing in what we used to train as a test, and it's just predicting everything accurately. So that's why this score is very high. Let's see if we can come up with the consistent metric. Okay, so we can see that it's predicting everything very accurately. It's predicting everything very accurately. Let me consult my book. Please, if you have any questions, please feel free to ask. No, that's about. Someone is asking, how do we get the iris data? It's embedded. So this is how I brought in the iris data. I brought it from our SQL library. That is how you can load it in. Then from here you can detach it here. Then it has two partitions. One is the data, one is the target, what we are trying to predict. So the target will go to the X, while the data will go to your X variable for training. So it's an inbuilt data set, and it's not that much. So you probably want to see if you can get the one that has much content. Then for this confusion matrix, the first row, is actually for the flower called, I think I wrote the name here, Tetosa. We have the second row, that is this one. So what is happening here is we've brought in the data set. It's actually an iris data set. It's small in length, as you can see, 150. We splitted it 80, 20% for training and testing. And we're using logistic regression, and we fit the model. Then this is where we do the prediction from our test data set. We are trying to use the model after training it to predict what the outcome will look like for the test data set.
Please, I have question concerning the confusion matrix.
Okay.
Sorry, I thought you for the confusion matrix we are supposed to have like two columns, then two rows. So like true positive, false positive, true negative, false negative. Can we, from this data now, from what you generated here, how can we deduce that from this array?
Good question. Let me see if I can put this in a color format. Just give me a sec. Yes, we do have all those stuff, but it's not that computer metrics expand beyond just four squares. You can have computer metrics as large as 8 squares. I've seen them before. And you could also have in mind that what we are classifying here is it's like a multi-classification where we have three sections. So what I'll just try doing is to see if I can plot it in the visual. Hold on, just give me a sec. Okay. Huh? Come here. I think it is better to reduce this. Okay, so for the first row, hello, can you hear me? Hello, can you guys hear me?
We can hear you.
Okay. So this is the first row. This is for Setesa. Where you see Setesa, those and it is saying it's actually the true positive. So this is the true positive. Every other thing, if you had maybe values here, it will be seen as false negative. Oh, sorry, false positive. But this is the true positive for Setesa. So there are no instances where the Setesa was incorrectly predicted as either a vesicolor or a veronica. There was no instance, which is a false positive for other classes. Then this second row, it predicted 9 instances as the vesicolor. You can see vesicolor, vesicolor. So it is the true positive. And if you check to this other side, there is no place where it predicted this vesicolor as maybe Setesa or Virginica. And this is actually like false positive, which is not true. Then the last line where it has Virginica, Virginica, this is a true positive. So it was able to predict. That's why I said this model, the data is very small, and right now everything is 100% accurate, which is as a result of overfitting it. So this is the true positive. Every other thing is false positive, and there are no false positive for each of them. Do you understand? So the idea about real conventional metric would always have four metrics. It's not always going to be, especially when you're doing a lot of multi-classification. And I've seen other models that classification model, the confusion matrix is beyond even the 3 by 3 rules you are saying. So it just as you expand your knowledge and maybe deal with large data sets or different kind of machine learning projects, you get to know that it's not just for so the true positive and false positive, true negative, false negative still stands. But it don't limit your mind to the whole false square. It goes beyond that. Do you understand?
Understood.
Uh, already running out of time. Does anybody has any? Let me check the chat box. I don't know. My audio should be okay by now. Does any other person have a question for me? Any question? Any question? We're already wrapping up. Any question? In our next class, today is just an intro. So in our next class, we'll focus more on the different metrics we have, the accuracy, the F1 score. We'll talk more about this in our next class and what they actually mean, and if necessary, the formulas. But this I gotten from the confusion matrix, the true positive, false positive, the true negative, and the false negative. But we'll talk more about that in our next class. Does anyone have any question on this? Okay, I'll assume that everybody understands. So it's not something too difficult. It's just a simple machine learning process with a small data set. So what you can do is to expand on it, get another data set that is probably large than this, split them into data and targets. So a target is just the column you want to predict, or sorry, you want to classify, right? Then you split them into training and testing. Then you train it, then you use it on the test data set that you try to you check the score, how accurate are they. Hopefully in our next class we won't have an accuracy of 1 so that we can explain more. Then we'll look at the classification report and how it's classifying it. Then we'll talk more about the confusion matrix and you see the ones that were classified as false negative and the ones that were positive. So you can just try it out using a different data set. Okay, just waiting in case anyone has any questions. Okay. Okay. Can someone drop a comment? Yeah, so the computer matrix is going to, yeah, like I said, show you what the prediction looks like. All right. Does anyone have any question for me? Okay. In the absence of no question, I'll see you guys in the next class. And like I said, we'll deal more on the evaluation metrics and talk about the computer metrics accuracy, F1 score, and just know more about them so that you know how to evaluate your model if it's performing well or not. Okay. Bye everyone. See you in the next class.
I'm sorry. Hello.
Yeah, I can hear you.
Okay. Unlike the kind of data sets I'm actually used to, we used to do a kind of exploration, like do describe info to see the details of the data that we have. So this type of data now that we import from sklearn, is there a way we can actually view the content or what the data comprises of? Is it just the flowers that we have? Is there any other things to describe it? Can we just view the data? That's just my question.
Yeah, I understand your question. I think what I would just advise you do is for you to to just drop it on the comment. It's for you to check out data sets that is embedded inside SQL and how you can access other features. And let me share my screen. There are a lot of them, even as it stands now, I may not be able to recall some of them. But yeah, let me just share my screen again. Can you see my screen?
Yes, please, I can see.
Okay. Already I used some of them here, but I would strongly advise you check the documentation for iris data, sorry, SQL data sets. And also I trust that we have more of them. I think we have the Boston data and we have some other, but some of the features you can access is maybe target name, what you're trying to predict. Then inside the iris data itself, you have it split by data, and that's the one we did already, where we split it by the target. So any data you're bringing from SQL, the first one is always the data, the second one is always the target. Let me explain. Are you saying this is a nested dictionary? So the first one is the data you want to train. It's a dictionary with a key and values. Then just inside it too is another one called the test. So that was how I was able to just yeah, this is the target array. Are you saying this?
Yes, I'm saying it.
Okay, let me do this. Iris just in case you are not too familiar, what you can do is once you just bring in the data set like I did like this, just run it this way, then go to the content. It's just a dictionary. So you can access the contents. Right now I want to extract this description. So I'm going to just do iris square bracket and description is to DESAR. I think I'm going to print it so that it shows very well. So this is what it looks like. Sorry, I didn't do this earlier on because of time, but this is what the description of the data looks like. So these are the three different classes, and these are the contents of the data we saw, the sepal length with petal length. These are like length of the flowers. They're using it to classify the the different flowers. So it's just 150, four numeric cues, the predictive and the targets. This is just a brief statistics about it. So this is just a description of the data set. I don't think there's any other content there. There's no other information here. Yeah. So yeah, that's how you can also do it to access it. Do you
All right,
understand?
thank you, sir. Yeah, I guess so. Thank you.
Right. Right, I'll see you guys in the next class. Okay. All right. Bye, everyone.